Well, my clock says it's 1 minute after 1, and we've got a lot of stuff to do today, so even before I get to the lesson material. So let me get started by sharing the syllabus. Let's see if I can find it. There it is. Okay. Is that visible to everybody?
Yes, I can see it.
Okay. Do you also see a little REC up in the corner or down at the bottom somewhere? That means we're recording?
Yes, it says recording up in the top left corner.
Excellent. I have a tendency to forget to start the recording, and that's not a good habit.
No.
Okay. Let's see. So this is what the syllabus looks like. These first few pages through page 3 are pretty much standard format for syllabi and courses at Southern. So they should look similar to this, at least the ones in the Department of Natural Arts and Sciences. And what you'll see is this catalog description and the prerequisites, those come straight out of the catalog, and there's no change in those guys. And these are the textbooks. I think most of you, all of you took my 213 class, so you should already have the textbook and the experiment manual. Of course, you won't need the lab coat, and you won't need eye protection. You will still need your scientific calculator. Okay. And this is where I start modifying. This is my stuff right here, starting on page 4. In this left-hand box is, like usual, my contact information, and you've probably seen all that before. The only difference is the office hours down here have changed. And they do every semester. So those are the times when I will be zoomed in automatically, and all you have to do is show up if you need help. And this is my ID. I use my New River ID so I can have office hours that are open to all of my classes, no matter where I teach them. They give you a personal ID with Southern, but I can't be 2 places at one time, so I'll just use this one. So if you have your Zoom client loaded on any device, then all you need is this ID, and you can join me at these times. Now, the first couple of weeks are going to be kind of sketchy because I've got some things that have to be done before the semester gets rolling too far. So it might be hard to find me there. So you may, if you need to get in touch with me, text me on the cell phone would probably be the best thing to do. Okay. And again, the slides are derived from the textbook that I use for New River, right? So they won't look, it'll be like 213. They won't look anything like the your textbook, Brown and others. But we cover the same material. There's your calculator. Everybody knows about scientific calculators and how you use them. I'm recording the session. I discovered this morning that I didn't have my Zoom account set up right. So it didn't record everything out of my morning class with Chem 203. So that's live and learn. But I've corrected it for this one, so we're going to get everything that I expect to get out of this recording. Obviously, you have a web camera and microphone already, so that's a non-issue. Let's see. Everything you're going to need is in Blackboard. I know, I think the last time we were together was face-to-face in the classroom, and I would generate hard copies for you. But now you got to go into Blackboard to get everything, which is not different as far as Blackboard goes, but we won't be meeting in person, so I can't hand out anything. We're going to be using the same type of lab notebook, right, the composition notebook. And again, since we're not face-to-face, I can't sell you a copy. So you got to locate one somewhere, either, well, I get mine from Walmart.
I have a quick question about that.
Sure.
Can we use like the same one that we used last semester, or do you want us to start a new one? Because that's fine, but I was just making sure.
You should start a new one.
Okay.
If you've tried several times and you can't find one, then let me know and we'll see what we can work out.
Okay.
That's an option, you know. I hadn't thought of that. If our back's up against the wall and you need to be moving on your labs, so if you can't find it in a week's time, before we meet next, let me know, and that's probably the way I go.
Okay. Thank you.
Let's see. Regular exams. These are native Blackboard exams, so we're not gonna have the hard copy type exams, whether they are hard copy or whether they're PDF files. These are going to be Blackboard native exams. So if you've ever taken a test in Blackboard, you're familiar with the process. The difference is that we're being proctored by Respondus Monitor and Lockdown Browser. So what that means is you've got to install the Lockdown Browser on your computer, and the details are in Appendix 3. You've got to go to a particular web link before you can download the copy of Lockdown Browser that is tailored for Southern. If you use any other, then it won't let you use it in the Southern system, because Southern has to purchase the service of Respondus Monitor Lockdown Browser from the company, and then they give you a special link that allows your students and faculty to access the browser from there. In fact, I probably need to install this myself, because the version I use is tailored for New River. So I won't be able to get into the, I should already have it actually, because I've set up the exams. They're already there. Yeah, so never mind. Let's see. So we'll look at that in Appendix 3 when we get down there. There's no final exam, simply because there's no time for it. The last exam you'll have is Chapter 18 exam. And Chapter 18 is, those are my numbers. Let's see, from my textbook. Let me see what yours look like. Yours will be Chapter 20 in your textbook is the last exam. And we'll look at the schedule in a minute, and then that'll make sense. But this last exam is going to be given during the finals week. And we don't have a final associated. There's just not enough room. I can't fit it in. Let's see. To get Zoom on your computer, Appendix 1 and 2 is applicable, and we'll look at that also. Formal lab reports. You're all familiar with how I like to see formal lab reports, and we'll look at that in Blackboard. There should still be an example lab report there. If you forgot, you should have old copies of yours, so you know, starting off, where you're likely to make mistakes, and you can correct them before they happen. Let's see. All right, here's the difference now. I had problems last semester with students procrastinating, both at Southern and New River. And they waited till the end of the semester to start writing their reports. And they were obviously rushed and sloppy and really not quality, not what the student could actually do. And it was hard to estimate whether they knew the stuff or not. So here's what I've done for this semester. And I'll show you in Blackboard. There's an assignment in there in each of the modules. And in order to access the demonstration video that I prepared for each of the lab exercises, since we're not there in person, I've performed the lab and created a video of the lab so you can see it being done. But you won't have access to that video until you submit photographs or PDF files or scans or whatever you can do of your lab notebook pages that pertain to that particular lab. So you submit those for grading, and if I grade them with 80% or better, then I'll submit that grade in the assignment, and it'll show up in the grade book. And then Blackboard system recognizes that input of the grade for the pages and says, okay, now it's time to open the demo, and it'll go ahead and open the demonstration. So when you submit them, it won't open up until I've submitted a grade. So we need a day or two lag times. You need to get those in as soon as possible. And that's another issue if you don't have a lab notebook, so we'll deal with that also. But, so how do you fill out your lab notebook? What am I looking for in your lab notebook to satisfy that 80% threshold? Each time you need an exercise title, right? You need an introductory statement on what you hope to accomplish in the lab, what it's all about, a section on safety concerns, a section with materials that are required to perform the lab, and then a step-by-step numbered procedure for the lab. And that's before, theoretically, before you go into the lab. It's set up that way. Now, when you actually view the video, you may see differences in the procedure. And that's when you have your lab notebook with you while you're watching the video, and you make those notations in the procedure. Because when you write the final report, you're writing in the past tense, and you're saying in the report, this is what actually happened, not what you wish happened based on the hard copy method. Okay? Then create a section in your lab notebook next for data and observations. It won't have any information, but it'll have places identified for information that you should be acquiring if you were in the lab, and particularly from the demonstration video. So those spaces need to be reserved, and then you reserve a space for calculations. It's not going to have anything in it unless calculations are required for pre-lab questions, right? So you'll have a section for pre-lab questions, and those you put the question in there and then the answer. So I want to see that. A section for discussion and for post-lab questions, those won't have anything in them either. The post-lab questions, you can write the questions in and leave a space, right, for the answer. But obviously, before you do the lab, post-lab, the answers don't need to be there. Neither does the discussion. So then, once you submit that and I grade it, and you get the 80% or better, then you have access to the demo, and you can go ahead with finishing your lab notebook. And then once the lab notebook is complete for that section, writing the report should be simple. Okay, let's see. I always tell my students also that the syllabus is the strictest possible presentation of the course. You know, for any of you who have kids or know people who have children, they will tell you instantly, when you lay down the rules for your children, that's as strict as they're going to get. You can't make them any stricter. You can loosen them up, but after you loosen them up, you can't strictify them anymore. So that's why the syllabus is, it's written like a contract, actually. And beyond that, we can loosen things up if we want, but we can't go any stricter than that. Here's the grading scale. It should be similar to the last time you took a course, 213. The exams are worth 80%. The laboratories are worth 20%. And out of that, the reports are 15% of the 20, 5% lab skills and notebook. That's mostly notebook because it's kind of hard to estimate your lab skills. But I left it in there anyway. So it gives me a little wiggle room. You know, if I think you're really doing well, only your grade doesn't quite show it, then I have an excuse for bumping it up a little. I don't like to use the word curve. That's a dirty word. Okay. Oh, I've got the next pages are landscape, so I've got to spread those out. There we go. So this is the schedule. And you should recognize the format. These are the lecture activities with the chapters covered. So all of this is actually lecture activities from these three columns right here. And right now we're in class business and discussion of the syllabus, and we're going to Blackboard. And then we're going to cover the topic of liquids and solids. Now in the PowerPoint slides, those will be designated as chapter 10 because that's what they are in my other textbook. But in your textbook, they will be extracted from chapter 11 and chapter 12. Okay, so it's actually 2 chapters for this one lecture. Then the next time we meet, we'll do chapter 11, which is chapter 13 in your textbook. And then on the following Friday, the 5th of February, we'll do the review. Like we always have. I'll field your questions if you have them, and talk about major topics and work some problems to try to get you ready for the first exam. Now, the first exam is on Blackboard, so we're not doing it in person. That means the exam is going to be whenever you feel ready. Typically, my students will wait until after their review is done, just to be sure they've got all their ducks in a row. And then anytime after the 5th of February, you know, the exam is open. With one proviso. I think I've put the exams on adaptive release as well. So I'll be able to determine that for sure when we get into Blackboard. But along with this, the labs, let's see. We should talk a little bit about safety today, but we covered all the safety topics in 213. So if we're short on time, we can dispense with that because you've already had the experience and you understand safety concerns. So these are the due dates. No, excuse me, I'm wrong. This first one, this is when you should be ready to access the material on February 5th, this #1 lab, and you will have presented me with your lab notebook pages, and I've cleared them and you're ready to go. So it should open up, should be open on that day. And then the report then is due on the 19th of February. So I've got these indicators in here when the previous lab is due. And they typically follow the pattern of whenever it's time to start this lab, the one before it is due. But I didn't want any confusion, so I stuck these little reminders in there as well. Okay, so that's the pattern. We won't meet on Friday the 19th of March because that's spring break. So you have a little bit of a gap there to finish up some things, to finish up the lab from number 3, which is due the day we come back. And I've also indicated which are formal reports and which are informal reports. So these in purple here are formal reports. 1, 2, well, this one's purple also. The informal report, I should change the color. It would make sense if I did that, to draw attention to this one is different than the others. So let me just do that right now. How about, green's too light. Let's try more colors. Instead of purple, if we did green, I'd want to make it darker. That's lighter, darker. How about that? That's about the same color as this one. That doesn't help much, does it? I'll just make it red. There you go. So that's an informal report. So what do I mean by informal report? It means that even though you filled out your lab notebook to perform this experiment, the actual report is completion of the document, the method document. And once you complete that document, you can turn that document in rather than the formal report. The reason I did it on the Chatelier's principle is just, there are too many things happening, and a formal report would be unwieldy. So I went for this route.
When we turn in those informal reports that we like fill out, do you want us to just scan them and email or turn them in? I mean,
you can. It should be a savable Acrobat form.
Okay.
So a lot of it you can type in and save the document. If there's anything that requires some handwork, it may be convenient to do the typing part and then print it out after that. And then the handwork you can do on top of that. Then you would have to scan it, whatever's convenient for you. Scan it or photograph it. If you can get it all into one document, say a PDF file, that would be great. It's easier to handle one file than it is 14 different images.
Oh, yeah.
And hopefully you'll be able to submit it in Blackboard. The hazard with sending it to me by email is that I get 100, 200 emails a day.
Yeah.
It's easy to lose it in the mix. But as a last resort, you can email it. Okay. And I'll always try to be on the lookout. If I don't see your report in Blackboard, then I'll go to my email and see if I can find it.
Okay.
Spring break is identified there. Okay, we covered that. And then this is the last day, April 12th, that you can withdraw with a W. I mean, if it comes to that, I hope it won't, but if it does, that's available. And then there's the exam 7, which is in the final exam week right there. And you don't have to wait till Friday to take it. Right? You can take it anytime that you feel comfortable. And then I have to turn the grades in on May 17th. If you have to contact me, let's see. It's always a good idea to check your email every day. And take a look at your grade book in Blackboard to see if I've graded your work yet. Because if you can't get to the demonstration video, but there's a grade in your grade book for those pages, then something's wrong and I need to know about it. But if you don't have a grade yet, then it's obvious that the video's not open yet. Okay, this is regular stuff. There's another withdrawal date. Let's see. You've seen a lot of this stuff already. I won't have to talk about plagiarism again because you guys have taken my course before, and that's really not an issue for this group. Exam etiquette. Okay, you're going to be videoed while you're taking the exam. If you've ever done the Respondus monitor, it's looking at you with your webcam, and it's doing facial recognition to see. You have to check in at the beginning of the exam, and it recognizes you, and you show it your ID, and then as you proceed through the exam, it checks to see if you're still there. So if you get up and leave, it's going to flag it for the instructor to take a look. Or if you are concentrating on a problem and like you dip your head down here to work on the problem, it's going to miss your face again. So it'll flag that. And all I do is just go in there and look at it, and I say, oh yeah, they're just working a problem, so no big deal, I'll pass it on through. But you also want light on your face. You don't want a bright background and a dark face. Otherwise, the system can't recognize you. And it actually, if it's dark enough, it won't let you start the exam. So don't sit in front of a bright window or a bright light. Okay, here's my how you get in touch with me for my office hours. There's my ID again. And here's where you download the Zoom client. Right? I think they have different versions for different computer systems. And for your phones, you can go to the, I guess for iPhones, you go to the iTunes store. For Android, you go to the, I forget what they call it, but you go to the App Store, and they should have the Zoom client there that you can load on your phones. And if you don't have to be in front of a computer, if you need to talk to me for just a couple of minutes and you're not home, then this works great. Okay, so now we're probably getting down to the appendix. Yeah, appendices, appendix 1. This is just how you set up and connect with the Zoom. And then the second one, this one is important, and I should have gone to this one first. Is how you set up your computer to do side-by-side. It's not as important now because the reason I want side-by-side on your side, I can't do it for you. You set up side-by-side so that you can size the screen and say put the shared screen on half of your monitor and put me on the other half. So I'm large enough so that when I start writing on this board, you can see it. If I'm just a little thumbnail up here in the corner, I can write all day long and it just looks like a blur. You can't tell what I'm doing. And I use this whiteboard. I don't use the whiteboard in Zoom because it's too clunky. It just doesn't work well. And it wastes a whole lot of time flipping back and forth. Because you can only share one screen at a time. And if I've got my PowerPoint shared on one screen, I have to stop that share, go to the whiteboard in Zoom, and then go back to the other share. And I'm not going to do that. So I've got this shared screen going. I've got me, hopefully, on the other half of the screen with my whiteboard. And that's the way it will appear when I process the recording and post it in Blackboard. It'll have shared screen on one side and me on the other. Okay, but this tells you how to do it. Once I've shared a screen, then you should be able to go into the Zoom desktop client and drop down view options, side-by-side mode. And you can do that every time we have a class, or you can set it up to automatically do side-by-side. And that's what these instructions down here are for. Automatic side-by-side. Okay, now here are the instructions for Respondus monitor lockdown browser that proctors the exams. You need a PC. Well, besides a reliable internet connection, everybody knows that. You need a PC, either a Windows or an Apple, or you can use a laptop. I've set it up to accept laptops, or an iPad. The one thing that it will not work with is Chromebook and smartphones. They don't have the functionality you need to complete the exam in using this monitor and this browser and Blackboard. They just don't like Chromebooks. Probably because Chromebooks don't store anything on themselves locally. It's all in the ether. Okay, webcam microphone is a given. If you got a laptop, you already got one built in. Let's see. They've got some videos that will help you with this. If you've never used Respondus Monitor Lockdown Browser, after you install the app and call it up for the first time, and what I've got in Blackboard is a practice exam. So you start up your browser, and then from the browser, you go into Blackboard. From the lockdown browser, you go to Blackboard. And once you're in there, then you take this practice test, and it checks out all of your features and runs you through a fake test. So I think there's one question, and it doesn't matter what the answer is because it doesn't affect your grade. So even if you get it wrong, it really doesn't matter. But it will check to be sure that you've got everything you need and you're doing everything in order, so that when you start a real exam, you're not fumbling around trying to get things to work. You'll already know it either works or it doesn't. And if it doesn't work, then we need to get it fixed before you waste time on an exam. Okay, so all of these next pages are, well, this first one right here, this link, this is the one that gets you the lockdown browser Respondus Monitor client that is particular for Southern. So you have to go to this link. Let's see, if you call up a document, sometimes you just say hold down the control key and it changes it to a little finger. If you hold control click, then you should be able to go straight from that link into to the website. Otherwise, you just highlight it, copy it, and paste it into your browser, and then go get it. But these are, I put these things in here in nauseating detail because that way I can answer most of your questions. All you have to do is just read through it. This is particular for iPad, right? So you have a different set of instructions for iPad because Apple doesn't play well with others. They have to be special. I've known that for 40 years. I remember when Apple computers came in a kit and you bought them from an electronics store and put them together yourself. And even at that time, they were too expensive. So I said, okay, that's all I can do. Can't own an Apple, they cost too much. Let's see. Okay, here's references the practice test right there, that top paragraph. And then this is what happens when you take an exam, either the practice exam or real exam. This is what you can expect. And I put this red arrow out here to draw your attention to one thing. It's going to ask you for a password, right? After you've gone into browser, lockdown browser, and then you've gone to Blackboard, you found your exam, you clicked on it to start, then it's going to ask you for a password. And I've tried doing it without the password in the past, and we run into problems. So I give it a password, and the password is always for me the course reference number, the CRN for that course. And in this case, it's 510, 510. The course designation is CH214, and the CRN is 510. That 510, it changes every semester. So that's what you use for your password. There's exam etiquette, right? Don't try to take the exam in your pajamas laying on your bed. Sit up in a chair with a dark background and light on your face, fully clothed, just like you were coming to class, and expel all small children and all animals from the environment, because they will cause the system to have fits. Now, we can make exceptions, of course. I mean, I live in the real world. If you have small children, they've got to be quiet. Because if they're small enough, they're not going to help you cheat. They're just going to distract you. Don't want any other adults in the room, definitely. Especially someone who's taken the course before. Okay. So I'll let you read the rest of that. That's the end of the syllabus, and we can go to Blackboard, and I can check out those other things to be sure that it's working properly. Let's see. I better pin myself back up here. There we go. Okay. So, and as always, you can stop me in the middle of anything to ask a question. That's why I use PowerPoints, for one of the reasons, is so I can be interrupted and then I can go back and pick up where I left off. Or I can digress and wander off in my storytelling and still come back and not miss any important information. Okay, so now I'm going to share, I think it's this one. Let's see, Blackboard, here we go. So let me call up, yeah, I'm not already in there. So this is, I'm an instructor, so you're going to see a lot of stuff here that you won't see in your class. You just need to find your course there. And this is what you'll see when it first pops up. And you have two start here's. I've got a start here for the lecture part of the course, and I've got to start here for the lab part of the course. Right? So we'll just take a quick look at the lecture, and I've got the course schedule there, first thing, so you don't have to go look it up. Does everybody remember what I was looking for? Oh, I remember. Never mind. Yeah. So here's where you get the syllabus and my course, my class schedule. So it'll tell you where I am and when I'm available. If I'm not in class and I'm not in office hours, you can still meet with me. I just need to know about it. And if we're going to meet by Zoom, you send me a time that's fits in my schedule, and I'll send you a Zoom invitation, and then all you have to do is click on it and connect. This is connection to free PDF readers. Right, so if you don't already have Adobe Acrobat Reader, which is free, then you can go to this connection or to a third-party reader at this one, which is a pretty good one. And when you install it, you probably already know this. When you install free stuff, you got to watch out for the stealth installs, because there'll be ghost programs that they'll want to install in the background, and usually you have to unclick them. They just automatically click. Okay, so let me go back. And I'm still in instructor mode, so a lot of the stuff over here that you're going to see, you won't see as a student, but I wanted to keep it in instructor mode because some things I can't show you as a student preview. Syllabus, free readers, lectures and reviews. So this all should look familiar, the way I set things up. So there's the, and these chapter numbers, I'm sorry, these chapter numbers are from Zumdahl. They're not from Brown. So you have to, if you need a correlation, you got to go to the schedule where I have them correlated. But this is the first exam, and I've got it set up so that I should actually have said exam 1, exam 2, exam 3. That's a correction I can make in the future. Oh, pardon me. All right. So say we go into this first one. All right. And there's everything from chapter 10 or whatever your chapter happens to be. The PowerPoints are all there, just like usual. Let's see. That one's grayed out, so this one is the one that's going to work. You won't have to worry about that because you'll only see what's available. And then reviews. Now, I've kept the reviews in here like we had with 213. A review document, the review key, and worked problems. Those are still good to do to help you for the Blackboard exam, because I created the Blackboard exam from my hard copy exams, right? So the question formats are exactly alike. So this would be a good place to review for an exam using these documents. It's not built up like a practice exam in Blackboard, but you still get the same question types.
Quick question about the
Yep.
exams. Like you said, the format's the same. On Blackboard, how will we work and show our work? Like the problems.
Yeah. You won't. Yeah. That's the trouble with Blackboard. It grades things for you, but it's where you have to work out problems, and I normally say show your work. You can't. It doesn't
Okay.
allow. It doesn't allow that. So I'll make allowances for that.
Okay.
And I think when I built the Blackboard tests from the hard copies, I didn't put anything in there that says show your work.
Alrighty.
So that shouldn't be an issue. I'm just hoping that you'll know how to do the problems and you're not just shooting spitballs. I'd
Okay.
prefer that you know how to work the problems.
Oh yeah.
Okay, what else we got? The reviews. So we got some this looks like a web connection here. I'm curious. Let me see. Yeah.
Grammarly can help you write quickly.
Okay. So that's a link to a video. Okay, so let's go back. Let's see. I need to find exams now. Here we have, okay. May 26th. I should have marked this one also as a previous semester. What I tried to do is any of the old videos that are in here from previous lectures or some that I may have ported over from New River, I marked those as previous semester. So if you don't want to look at the old stuff, then you don't waste your time searching around for the current video produced from what we're doing today. But this one is from May 2020. I should mark that one also as a previous semester. So that's one thing. In fact, I'm going to make myself a note to check videos in previous semester. Yeah. So I can go in and correct that. And then when you see one of these web links to the video, which I post on YouTube, so you could go straight into YouTube if you want. And you can see everything I've ever produced. So I'll mark that as previous semester, and then you won't have any trouble finding what you need to find. Okay, so that's all lectures and reviews. Okay, and that'll be the same format for each one. It'll go down through here and give you things that you might need, including the videos and the reviews and the PowerPoints. It's standard format that I've used forever. And then I put the exams in a separate folder, I believe. Where are they? Here they are, Blackboard exams. Okay, see that these are grayed out. That's because each one has, okay. All right, hold everything. Dick Tracy calling headquarters. That's an old cartoon I used to watch as a kid. And something serious would happen. Dick Tracy, this cartoon character, would say, hold everything. Dick Tracy calling headquarters. And he had this like a little cell phone or walkie-talkie on his wrist, and he'd talk to it. Anyway, the exams are not set up to release in sequence. Like in other classes, you have to complete exam 1 before exam 2 opens up. But in this class, what I've done, and especially since we only have 3 students, I've just put dates on them. Right? So this one will open up on January 29th. So let me see. Let me look at my schedule. January 29th. Oh, wrong page. Sorry. January 29th. Okay. January 29th is the day that I introduce Chapter 11. In fact, that's next week. So that exam will open up on a time schedule, not on a logical schedule. In other words, it doesn't say, has this student completed exam 1 before they can do exam 2 and 2 before 3? I just open them up on a time schedule so you can see that they open up. And I think the pattern is whenever the last chapter in that exam is presented on that day, that exam will open up. That's just to encourage you to do them in sequence rather than procrastinate, miss 2 exams and say, oh, this one's due, so I better do that one now and go back and get the others later. By the time you get to this exam, if you haven't done these 2 exams before it, then you're in pretty bad shape already. And if you've ever done that, you know what I'm talking about. I've got a final exam down here, but there's no time to do it, so you won't ever see that one. And I'm sure everybody is brokenhearted about that. I know I would be, because I like final exams as a student. Okay, so that's everything on the lecture side. I think these guys down here, you've probably seen these before. These were the ones where you had to complete the hard copy and submit it. I could have done that. The problem is I've got to grade those things by hand. And my schedule is full this semester. Any help I can get from a system doing the grading for me, I'll take it. And then if there's a problem, I'll look at individual grading issues. Like if you see that you've been marked wrong on one of them, and you think that it should have been right, then you can contact me. Even after it's graded, you can contact me and tell me which one it is. You need to be specific with the question wording, because the numbering, they're randomized. Every time the exam opens up for a different student, the questions are randomized. So you need something else to tell you what question you're referring to as an issue. Then I can find it and say, is there an error? I'll look in Blackboard and say, okay, this is the answer Blackboard expects. And I can say, yeah, that's right. And I have to give you the bad news. Or I could say, no, I checked the wrong one there. That should be this one. And then regrade and manually input your grade with the correction. That brings up another topic. While you're taking exams, suppose you lose your internet connection or the power goes out, because it could do that this winter, especially if your internet connection is not that reliable. So what do? Well, if it goes out, before it goes out, what you need to do is to keep track of your answers in such a way that even though they're randomized on the next time through, you can put the answer in. You can put the answer that you calculated before. How you do that is up to you. You could write in detail and put the answer, or you could just have a list of answers. And then, since they're multiple choice, usually, I think there's some fill in the blank, but most are multiple choice. Then you could look at the question and say, okay, there are these choices. And you should look down and say, well, that's the only one that fits in that group, so that must be the answer. The other option, I have enabled Lockdown Browser. See, Lockdown Browser, what it does is it shuts you out of surfing the internet, right? And going to programs that are on your computer. It locks you in. That's why I call it lockdown. You're locked into that browser while you're taking the test. But it allows the instructor to permit printing the screen. You can print that screen. So when you got all your answers on a screen, before you scroll to the next one, you can hit the print button and it print out a copy and you got your answer. So if the power goes out, you're good to go. You just want to be sure that your printer has fresh ink cartridges. You don't want to run out of ink in the middle of an exam if that's your method. Okay, so now to the labs. And I put another schedule, the same schedule, in the lab side, so you don't have to go flipping back and forth. And you will start lab number 1 on February 5th, because at that time, you should have had time to read, study, prepare for the exam, and the material that you need is in your head and ready to do lab 1. Plus, it gives you time to fill out your notebook, scan it or photograph it, submit it, get a grade, and you're ready to go. Here's safety issues. I didn't do a lab safety contract because you're not going to be in the lab anyhow. So this is laboratory safety for students. You can read that at your leisure. It's good information. Okay. I will have a first lab notebook check, just like the last time we had in 213. And this is all I'm looking for. On the front cover, you'll take a picture of that, and I'm expecting to see on the front cover your name, the course, and the semester at a minimum. You can put anything else you want, but those 3. Then you need to go through and number every page, just like before, from 1 to probably 200, I think. And every right-hand page is going to be odd. Every left-hand page is going to be even. And when you start filling out your notebook, in the beginning, you only write on the odd pages, the right-hand pages. And leave yourself some space, right, for corrections. And then the left-hand side of the page, of course, you can use that for any mega corrections or for other things that you may want to put in there, like a graph. You may want to draw a graph, or there's not enough room on the right-hand side to put some cut and paste thing that you want, so you can stick it on the left-hand side. For your first lab notebook check, of course, I want to see the front cover, the table of contents, a page from the middle of the notebook, and the last page. That's it. That's all I need for those. And once those are done, then let's see. Then the lab exercises, I believe, are keyed to, yes. So here's how they're keyed to open. Here's where you put in the lab notebook pages. This is an assignment. You can tell by that icon on the left. That's for assignments. So if you go in here, see, this one's not visible yet. Shouldn't be. You go in here and notice there's really no assignment. There's no hard copy in this one. All you have to do is take those pages and submit them right here, attach files. So if you can get it done in one PDF, fine. If you have to submit individual photographs, okay. If you got an Android phone, I think I may have told the class in 213, you can use Cam Scanner for Androids, and it will take pictures and compile them into a PDF. I think iPhone is supposed to have a native app that will do that. And then once you've submitted them, then I have to grade them. And once the grade appears, then we'll breadcrumb back here. Then this will open up. Now let's see if I'm right. So let me go down and go into student preview mode, and then that means I've got to go all the way back down to the lab exercises. And let's say we were in this one. Let's see. Oh, okay. Then the video will open up. I was confused for a second. This one's already open. This is like a preliminary, talking about how to use Excel to find the freezing point. You don't have to use the Microsoft Excel to find the freezing point, but if you want to, that's how you do it. So let me go back, exit preview. So I should be able to see the video as instructor. Yeah, here's the demo. Only this little thing down here, you won't see this, but adaptive release, that's the method that I can use to say, don't release it until a certain condition is met. So that demo won't be available until you get a grade for that one. But this one is already open, and that makes sense because you got to set the lab notebook up and you need something to go by, so there it is. Okay, so that's how the lab exercises are arranged, and there are only 1, 2, 3, 4, 5, 6 of them. Yeah, I've got 6. So it's not overly taxing. Let's see, Le Chatelier's principle was an informal report. Electrochemistry is an informal report too. In fact, I haven't even shot that video yet. I've got 2 more videos to do, and then we'll be set. I got to do one for complex ions, and I got to do one for electrochemistry, and they were good. I did this one yesterday here on the New River campus because Southern is locked down, and I have to ask permission anyway, so I might as well keep it close to home. Okay, so that's lab exercises. Let's see if there's anything else in here of interest. Lab exercises, lab notebook and reports. Okay. There's how to keep a notebook. There's another thing on lab notebooks. Sample lab report. Here you go. So I gave you this you probably remember this one from previous semester. Common errors in preparing a lab report, just as a reminders. The grading rubric. Let me see if that's the right one. Yeah, 214.510. Okay, so that one's current. Extended characters. We talked about that last class we took. Let's see. Let's see if this one. I'm curious which one this is. Waters of constitution and hydration. Okay. So we did that one in 213, I think. And you probably already have a graded version, so you know where your weaknesses are. Okay, what about this one? Example lab notebook. Yeah, okay. So this is what I would expect to see in a lab notebook. There's the front page, table of contents. This student put the beginning and end pages. You don't have to do that. Just put the beginning page. It's a little overkill, but it's not bad. And then they started on page 5. Okay. So what am I looking for? I've already said that, haven't I? What I'm looking for in the pages. Yeah, I know I've already covered that. Okay. Let me back up and see if there's anything else. I think we've covered about everything there is. There's another connection for PDF readers, just in case. And here is a little blurb again on what I'm looking for setting up your lab notebook. Right. So there's redundancy built into the system. Okay. It's right at 2 o'clock, and that gives me an hour to finish my chapter 10, your chapter 11 and 12. So if you have questions, fire away. Otherwise, we'll move on to liquids and solids. And the pattern is going to be the same. The course officially, the lecture part of the course officially ends at or about 3 o'clock. Clock's 2, so that gives me an hour. If I get long-winded and I go over, then, and you have other obligations, then you can close your session and come back and look at the rest of the video later. But I'm going to finish the lecture, whether you're here or not. Okay, so let me share the PowerPoint. Here we go. And now I want to turn that into a slideshow. There we go. So everybody should see chapter 10, liquids and solids. And this is what my textbook looked like that I used at New River. And it corresponds, like I said, to chapter 11 and 12 for your Brown. I never did get a hard copy of Brown. I think I downloaded an internet version. So I was able to make the correlation between the topics covered. All right. So let's look at, ideally, we're picking up where we left off in the Principles of Chemistry 1. This is Principles of Chemistry 2. And I think we left off with bonding. We did ionic bonding, and then we did covalent bonding at the end of that last semester. And we talked about the different theories for explaining the bonding, right? And we finished up with molecular bonding theory. So now, those were bonds inside the molecules, holding the atoms together. Now what we're going to look at is bonding between molecules, because contrary to the kinetic molecular theory, okay, that brain freeze there for a minute. Contrary to the kinetic molecular theory, these molecules are not just billiard balls bouncing off each other. They do interact. So real molecules do interact. They either repel, they attract. Some occasionally don't interact very much. And we're going to look at those as versus the intramolecular bonding, which we discussed at the end of last semester. The bonding is either, well, the strongest bonds are between atoms that share electrons. Ionic bonding is weaker, actually, than covalent bonding. So we're going to look at intermolecular forces, that is, forces that hold molecules together or influence the way they interact. And they come in basically two flavors. There are dipoles, and I'm trying to scratch my head, trying to remember if we introduced the dipole concept. I don't, maybe we did, maybe we didn't, but it would be good to review. A dipole, I think of a magnet. Magnet has a north and a south pole. It's not electrostatically charged, right? Otherwise, if you touch one end, you get a shock. It just has north attraction, south attraction. So south attracts north and north attracts south. In a molecular dipole, the molecule is polarized in such a way that the electron density in the molecule is unevenly distributed. So usually one side will be slightly more negative and the other side will be slightly more positive. Now I say slightly because it's not a division of charge enough to create an electrostatic effect. Well, it is an electrostatic effect, but it's not a complete charge like you would have on a, if you took a neutral atom, like an oxygen atom, and you add 2 electrons to it, you get a 2- charge, which is typical for oxygen when it when it ionically bonds with some metal. So how does that work? Well, if the molecule has a dipole and it's unbalanced charge, then when it encounters another molecule, right? So that's electron density. So we're going to have like that. Slight negative on this end, slight positive on that end. When it encounters, say it's a pure substance, it's only that molecule in the substance, they're still going to interact. So this one will have and there'll be an attraction. It won't be an attraction that is as strong as an ionic or covalent bond, right? It's too weak for that. So it's in this case, it's a dipole-dipole. The dipole from that one attracts the dipole from that one. Okay? So it's inherently weaker than the covalent or ionic bonding. Now there's special types, cases. Well, before I do that, you can have a dipole for one molecule interacting with an ion. So, and that's what you do when you put sodium chloride into solution in water. You get the ions of the sodium ions and chlorine ions interacting with the water molecules. So you've got ions interacting with a polar molecule, which is water. So you get dipole ionic forces. Well, there's a special case of dipole-dipole interactions, and these are on a spectrum of strength. So you can have very weak dipole interactions, depending on the molecules. You can have very strong dipole-dipole interactions. And the strongest are a special kind called hydrogen bonding. And water is the best example for hydrogen bonding. you find that, let's see. Yeah, we've talked about electronegativity. Okay, good. Oxygen is more electronegative than hydrogen, so it's going to draw electron density toward the oxygen and leave, actually that'd be 2, and leave a slight positive charge on the hydrogens. Well, this can happen with oxygen and hydrogen. It can happen with fluorine and hydrogen. I think even sulfur and hydrogen will do it. Any molecules that have those combinations, they call it hydrogen bonding. The hydrogen always has to be there. And what happens is, any other molecule, like this one, will form an attraction bond. And the hydrogen bond is the strongest of the dipole-dipole interactions. Okay, it's still dipole-dipole, but it's a subcategory. Now, what if you don't have a polar molecule? Or, better yet, you just got atoms. How do they attract one another? Let's say we have, a noble gas that we have cooled enough to liquefy. Well, why does it form a liquid? Well, the forces holding the noble gas atoms together must be strong enough to overcome the energy that's added from the environment. Right? But noble gases, I mean, it's a single atom. How are you going to get a dipole out of a single atom? You don't, right? But you can get instantaneous redistribution of electron density even around a noble gas atom. And it's more pronounced the larger the atom, right? Because they've got more places to be. So let's say xenon, for instance. Okay, there's your xenon atom. So what happens? Well, for a very instant, you get a redistribution of electron density to one side of the xenon atom. What does that do in terms of the other xenon atoms? Well, when this xenon atom, when it sees this one, and that's positive, that positive attracts electrons. So it responds by redistributing its electron density, right? And now, even for a microsecond, you have an attraction. That's called London Dispersion Forces. London, not named after the town, named after a person. And dispersion means the electron density is dispersed instantaneously, long enough to give an attraction. So that's why noble gases do attract one another. We know because they condense. If there was no attraction between noble gas atoms, it doesn't matter how cold you get them, they're never going to condense into a liquid. So there has to be some attractive force. And that's one of the evidences for London dispersion forces. Okay, I spent a lot of time talking on that, so we can skip over some of these slides. So this is what water looks like with hydrogen bonding. The intramolecular bonds are always stronger than the intermolecular bonds. Those that hold the molecule together are always stronger because the molecule behaves as a single unit. If it didn't, then these other forces wouldn't matter. It would just fly apart. And that's what this little paragraph says. Actually, it's one sentence. Okay, evidence for these attractive forces I alluded to with this discussion have to do with phase changes. Why do substances either molecular or elemental. Why do they attract? Why do they attract one another? How do we know? Because phases change. If there's enough energy being put into the system to break these bonds, then xenon's a gas. And believe me, it doesn't take much. It's way down in the negative centigrade to liquefy these things. What you have to do is reduce the kinetic energy, the temperature of xenon, to the point where there's not enough energy anymore to break those London dispersion forces. So that's what we're trying to show here. In a gas, the forces are not strong enough. The temperature, the kinetic energy of the atoms or the molecules is just way too high. You got to start cooling it down, adding pressure, getting them close together with low energy so that they can start to attract one another. And when you do that, they turn into a liquid. If you go even further, they'll turn into a solid. You just reduce the amount of exterior or the kinetic energy of all the molecules in your substance, and then they slow down enough to where these intermolecular forces are strong enough to attract them together. And that's what I'm saying here in this slide. So I'm going to skip that. Now, one of the things that we do know about solids, liquids, and gases is the distance between the molecules decreases as we go from gas to liquid to solid. Now, the largest difference in distance occurs between gas and liquid. But we also have an indication of that from studies of density. Normally, when you go from a gas to a liquid to solid, the density increases. We're going from 10 to minus 4 down to 1, basically. So the density is increasing because the atoms and molecules are getting closer together. They occupy less space with the same mass, right? So remember the definition of density, right? If the mass stays the same, but the volume gets smaller, then the density goes up. Now, water's a bad choice here because it behaves, it's kind of funny. When it goes from liquid to solid, the density decreases, which means the molecules are getting farther apart. Well, there's an explanation for that too. As water goes from liquid to solid, as a liquid, the water molecules are moving past one another. There's no regular structure. But when you go to a solid with water, they tend to form a hexagonal shape with a water molecule at each one of these apexes. So what does that do? Well, it opens up the lattice and leaves empty space in between. So that's where the increased volume comes, consequently decreased density. So water's kind of funny that way. Actually, it's a good thing it is, right? If water followed the same pattern as most gas, liquid, solid transitions, the solid would be more dense than the liquid. And when the ocean started to freeze at the top, the ice would drop to the bottom, and they just keep freezing until the oceans were solid ice, and they'd stay that way for millennia. So it's a good thing that this happens. So you get a crust of solid water, ice, on top, which insulates the water below. So any animals living in the water, all they have to do is just go a little deeper, and it gets warmer, actually. So that's neither here nor there for chemistry's purposes. Dipole-dipole forces. Okay, I discussed how dipoles are created, sort of, but I want to be more specific now. In order to determine whether a molecule is polar or nonpolar, right? Does it have a dipole moment? Is it negative on one side, positive on the other? You need to know two things. Number one, does it have polar bonds? And to do that, you need to compare electronegativities, right? For water, oxygen is more electronegative than hydrogen, so it draws electron density toward the oxygen, right? Number two is best illustrated first. So let's say we had oxygen, and instead of drawing it like I did, actually, which we determined when we did VSEPR modeling, right, valence shell electron pair repulsion, we determined that water was bent, right? But what if it wasn't bent? What if it was actually like this? Oops, that didn't work. Right? So you'd have a dipole moment this way and a dipole moment this way. Right? That's how we draw dipole moments, with an arrow and a plus on the end. This is the plus side and this is the negative side. In this case, they would cancel each other out and water should be nonpolar. And at 1 atmosphere pressure and normal room temperature, water would be a gas. There would be no liquid water on the surface of the earth. But in fact, water is bent. So this dipole moment for each of the bonds, when we sum them up using vector summation, we get a dipole moment that way, okay? So the second thing you need to know, after you know the bonds are polar, you need to know the geometry of the molecule. Once you know those two, then you can determine if the molecule is polar or nonpolar. If it has polar bonds, but they're symmetrical, then you have a nonpolar molecule. Let's see. Okay, here's some other choices. All right, sulfur's not in there. Nitrogen. Nitrogen, oxygen, fluorine with hydrogen will give you the potential for hydrogen bonding. London dispersion forces, we talked about those already. Actually, we talked about them in terms of noble gases, but London dispersion forces can occur in molecules as well. And in fact, I forgot to write that one up there. Let me do it again. Two things you need to know. Polar bonds and geometry. Okay, that's how you determine polarity of a molecule. Now, London dispersion forces can occur in large molecules as well. Well, small and large molecules. But the best sequence that I can think of and display of London dispersion forces is in the series of hydrocarbons. Okay, what's a hydrocarbon? Hydrocarbon is a molecule that has carbon and hydrogen, that's it. Okay, and the homologous series of hydrocarbons goes like this. You got methane, you got ethane, you got propane, and you got butane, and you got, they get larger and larger and larger. For these, London dispersion forces are not as important. Methane is a gas at room temperature. So is, see, methane, ethane, propane. Butane is a liquid under pressure, but in the butane lighters, once you release the pressure, you get gas. But when you start getting into larger molecules like octane in your gas tank, or C12s, C10s and 12s and 14s, you're talking about diesel fuel. Okay, why do they form a liquid, right? Because their structure is like a series of carbon atoms and then hydrogens all the way around. Well, it turns out that the carbon-hydrogen difference in electronegativity is very small. So there's not much polarity to work with there. So the attraction of one molecule to the other is dependent on how strong are the London dispersion forces. And the London dispersion forces in a large molecule are more easily maintained than in smaller molecules, because you can get positives way down here and negative way out here. Or they can ripple down the molecule. And you have more opportunity for interaction between the molecules when they're big. So the larger the molecule in this series, the higher the boiling point, because of London dispersion forces. Okay, this is a good point to make. London dispersion forces occur in all molecules. Every single one experiences London dispersion forces. Nonpolar, polar, all families. The question is, since they're so weak, what other forces are being imposed on that molecule? If they're strong enough, London dispersion forces, even though they're there, don't matter. They're too weak. Okay, in general, we can also infer strong intermolecular forces if the boiling point and melting point of the substance is high. Now, that's for covalently bound molecules, right? We're not talking about ionic here, right? We know that melting points for ionic solids are very high because they have lots of positive negative interactions. But for covalent molecules, as the intermolecular forces increase, the melting points and boiling points are higher. And I just referred to that with water. If water didn't have these intermolecular forces, it would be a gas. But since it does, we've increased the boiling point and the melting point of water to the point that it's usually liquid on the surface of the earth, sometimes solid, sometimes gas, but most of the time it's liquid. Okay, these are series of hydrides of the various elements. So what we see is you need your periodic table. And, well, I'm missing mine. It used to be right here. Where's my periodic table? Okay. I guess I'm going to have to print another one. So, on your periodic table, oh, there's one. I have to reach for it. Let's see here. Okay. Here we go. Yeah. Here's my periodic table. So we've got, let's see, there it is. We've got carbon, and then we go down in that family to silicon. Then we go down to germanium, and we go down to tin. What we're seeing is the boiling point increases as we go down the series. Now, why is that? Well, these this hydride, which is methane, is a gas. But when you go to silicon, the silicon atom is bigger, makes the molecule bigger. And it's the same idea as when I was talking about the noble gases. As they get bigger, there's more room for distribution of electron density, so the London dispersion forces become stronger. So as we go down, we get bigger molecules, stronger forces, higher boiling point. Let's see, where is it? Higher boiling point. Okay? Now that doesn't work for all of them. For these other series, where you're starting with phosphorus, chlorine, and sulfur down here, then from there down, the trend works. But in this second period, what we're finding is that they kind of not, other types of interactions are involved. Okay, so London dispersion forces are active here, but over here, the dipole is stronger, right? And if you remember when we drew ammonia, NH3, it had a lone pair electron on one end. So that automatically gives it that distribution of negative on one side of the molecule, right? HF has a stronger dipole interaction because the fluorine is a very small atom, and it's more electronegative than hydrogen. It draws electron density away from hydrogen very strongly. It makes for high dipoles, right? Even hydrogen bonding. And then water, of course, we've discussed ad nauseum. Okay, this dotted line is just to illustrate that if this trend were obeyed by the hydrides of the chalcogen family, then water should be down here, and its boiling point would be below 0. But nope, don't work that way. Okay, now set that aside for a second. Now let's see if we understood what has been presented. Which molecule is capable of forming stronger intermolecular forces? So you can look at it two different ways. If we look at it in terms of boiling point, we can infer that the stronger intermolecular forces are with water, because its boiling point is 100 degrees and nitrogen's boiling point is minus 195 degrees centigrade, Celsius, right? So we can infer from that that water has the stronger intermolecular forces. Or if you look at the structure, you find that dinitrogen is nonpolar based upon there's no uneven distribution of electrons, right? Nitrogen versus nitrogen, they pull evenly. And while hydrogen is a bent molecule with different electronegativities. So that works also. But the answer is still the same. Water has the stronger intermolecular forces. Okay. The structure of the molecule makes a huge difference also. Notice that C2H6O is the molecular formula for two different molecules, right? If you don't know the structure, you really don't know which one you're talking about. One of them is this one. It's ethanol, the drinking kind. The other one is dimethyl ether, right? So which one would you think has the stronger intermolecular attraction? Well, you do have some dipole here, right? That bond and that bond, but look, they're symmetrical. So they cancel one another out. So this molecule is nonpolar, but this one has oxygen and hydrogen on the end. So you can get a hydrogen bonding situation out here with any other molecule that's in solution. So you would expect that the boiling point for the ethanol to be higher than the ether. Okay, we're relying on discussion here. There's no animation involved. Okay, which gas would have more ideally would behave more ideally at the same conditions of pressure and temperature? So the question is, what do we mean by ideally? Ideally refers back to the kinetic molecular theory, right? No interaction among the molecules of a substance, right? They just act like billiard balls. That's ideal behavior. So what we need to do is just say, all right, which one has intermolecular forces that are strong enough to influence its behavior? Nitrogen doesn't. It's a nonpolar molecule. So the only thing it has is London dispersion forces, which are very, very weak. But carbon monoxide has a difference in electronegativity, plus it has lone pair electrons situated on the oxygen. So it does have a dipole moment. That means that the more ideal behavior comes from nitrogen. Okay, and there's your explanation. Okay, characterize. I know I'm going to run out of time, so I'm not even going to try to rush. Liquids have low compressibility. What does that mean? That means when you squeeze it, it doesn't get any smaller in general. Now we know from measurements that have been made of water at extreme depth, like 2, 3, 4 miles deep, we do find that the density of water deep, even though it's liquid, is still higher than it is at the surface. So they do have some compressibility, but it takes a lot of pressure. So typically they have low compressibility. They lack rigidity, which is another way of saying that they don't hold the shape. The liquids assume the shape of the vessel. And compared to gases, they do have high density. In fact, they have density that's very close to the solid of the same substance, with a few exceptions like water. Liquids also exhibit surface tension. What do we mean by surface tension? Well, in a liquid, a pure liquid, say, the molecules, whether strongly or weakly, attract one another in the body of the liquid. But at the surface of the liquid, see, we've got molecules down here, down here, down here, surrounding each other, and they're interacting, okay? But at the surface, they can only interact with their neighbors. So any attraction, and you don't lose the attractive ability of a molecule just because it's at the surface. It still has the strong attraction, and it's got to attract something. So the attraction here at the surface is stronger than it is below it. And it causes almost like a film at the surface. If you take a nice dish of water and you let it settle down for no vibrations, and you don't live in an earthquake zone, and then you take a needle and you're careful and you get very close to the water before you release, then the needle will sit there on top of the water, will not sink. We know that the needle is denser than water, so it should sink. There's something holding it up. Surface tension. Those molecules at the surface are more strongly attracted than in the body of the liquid. So some of that force is expended in holding that needle up. Large intermolecular forces tend to produce higher surface tension, and water is a perfect example. There are some creatures in nature that take advantage of surface tension. You can see them sometimes in the summer. You see them scooting across the surface of water. They're not floating. They're not using buoyancy. Their feet spread their weight out over a large area, and they are using the surface tension to hold themselves up. I think one of them is called a water skimmer, and they'll go faster than you would expect. How about capillary action? All of these phenomena we're using to illustrate and actually prove that these microscopic interactions do occur, and we're using macroscopic evidence to support our theory. Capillary action. Capillary action is the movement of a liquid up a very narrow bore tube. Okay, so there's a wide bore tube and a narrow bore tube. So what's happening? Well, you have a competition within the liquid and between the liquid and the walls of the tube. There's a competition going on between cohesive forces and adhesive forces. Cohesive forces are those that attract the liquid to itself. That's what the co means, cohesive. Adhesive means other. So these forces are attractions between the liquid and the walls of the container. All right? So if we put a liquid here, we would expect it to be right here, right there. But in the wide bore tube, you may get, oh, very slight rise, maybe not even any. And there may be some attraction on the walls. But in the capillary tube, it may rise up to here. Okay? Now, why is that? Well, there are cohesive and adhesive forces. So the adhesive forces would be between the liquid and usually a glass tube, because you want to see what's going on inside. If you use a metal tube, you wouldn't know it's happening. So the attraction between, let's keep it simple, between water and the glass, the attractions are there, right? So let's take it on a step-by-step process. So first what happens is the water is attracted to the glass. So it tends to rise up on the sides, like that, right? More water attracted to the glass makes it bow up like that. But there are cohesive forces at work also. So the cohesive forces try to draw the water together, and that takes the bow and flattens it out. So it moves up here. And then it just keeps doing that until it gets to that height. Now, what makes it stop? Well, the forces required to get it up there are now balanced by the mass of the water above the surface. So at that balancing point, you get a fixed height. So if the force is depending upon the mass of the water that's being held up, the narrower the tube, the higher the liquid will go. Because the narrow tube means that the cylinder is smaller diameter surface area. So to get the same amount of water, or yeah, in this case, you need a taller cylinder. Okay. So the narrower the tube, the higher it rises. Now, that's for cases where the attraction, where the adhesive forces exceed the cohesive forces. Otherwise, it wouldn't be able to draw it up like that. Now, in the case where the cohesive forces are stronger than the adhesive forces, instead of getting a concave meniscus, you get a convex meniscus. So in the case where you have mercury and you have a tube, the mercury, however high it may go, will be like this. And that just is an indicator that the cohesive forces between the mercury atoms are much higher than the adhesive forces between the mercury and the walls of the container. And really the only thing holding it up there is if you have a vacuum up here. Right here. And then the thing that's holding it up is air pressure. That's how a barometer works. Okay? In this case, adhesive forces are stronger for water and glass. Now, why is that? Why would water be attracted to glass? You know what glass is made of? Sand, silicon dioxide. So on the surface of the glass, you have oxygen sticking out there. Some of them, not all of them, some of them are silicon, some are oxygen. Well, what does that do? Well, oxygen tends to be electronegative. In fact, it's up and to the right of silicon, right? Remember? Lower left, upper right, increased electronegativity. So here's silicon, there's oxygen. So you're going to get a slight displacement of electron density toward oxygen. And that makes it like that. So here's your water attracting the water atom, the water molecule. And combined on the surface, you get a stronger adhesive attraction between the water and the surface of the glass than you do between water molecules inside. Okay. So I got about 12 minutes left, and then you guys are probably going to split, and I'll just keep talking. So what's another indicator of these forces, the intermolecular forces? Viscosity. Viscosity. What's a viscosity? That's a word that indicates a liquid resists flowing. So the very non-viscous liquids, like water, or like, oh, what's another example? Pure alcohol, pure ethanol, 100%, crystal clear. Those liquids flow easily. Other liquids don't flow as easily, like solutions of sugar and water. Honey, for instance, very, very high concentration of invert sugar in water. They're very viscous. They resist flowing. So you can test that one way or another. You can like let the liquid flow through a small orifice, see how fast the level drops, you know. Or you can drop a standardized projectile into the liquid and see how far it penetrates. And that's also an indication of viscosity. There are a number of different methods that companies have used to create viscometers. The viscosity implies, high viscosity implies large intermolecular forces. The higher the forces, the stronger the forces between molecules, the more viscous the liquid. So as you cool a liquid down, you remove that kinetic energy from the molecules, and now the intermolecular forces can do not have as much kinetic energy to overcome. They become stronger relative. So as you cool them down, they become thicker, more viscous. So what do you do when you want honey to flow fast? You heat it up. If you want it to be solid, you cool it down. You know the difference between pouring molasses on your pancakes. If the bottle of molasses has sat on the counter for 2 or 3 days, it flows pretty easy. If you stick it in the refrigerator and pull it out, you turn it up, and you're still waiting for it to come out because it's cold and the intermolecular forces are predominant. Okay, let's talk about solids now. We've talked about gases, liquids, now solids. We can characterize solids in roughly 2 types. Let's start with the second type, the crystalline solid. The crystalline solid, the atoms or molecules in the solid are in regularly arranged structure. And we call that a crystal. One of the most popular crystals on the planet now is the diamond. It's a regular crystal structure of carbon atoms with occasional impurities, but for the most part, it's just a lattice network of carbon. It's a very ordered structure. And because it's ordered, it can be explained in terms of what we call unit cells. That is, you can, even if it's not pure carbon, say it's something else like sodium chloride, will form a unit cell. And the unit cell is the smallest part of that crystal that still retains the network structure of the crystal. And then to obtain the larger crystal that you may have in your possession, you just repeat that structure over and over and over and over and over again. That's the unit cell. On the other hand, amorphous solids do not have that structure. They're characterized by disorder. Even if small parts of the amorphous solid may be crystalline in nature, they are irregularly distributed, heterogeneous. Glass is a perfect example of that. And when we say glass, nowadays, you've got to be more specific. What type of glass? Right? Because there's so many different types. Our cell phones are, their screen is covered with something called Gorilla Glass, which is extremely tough. But glass is an example of an amorphous solid. In fact, some researchers prefer to call glass a supercooled liquid. Potato. It's a solid. It holds its shape, and it has a definite volume. So it's a solid. Okay. The unit cell, we said before, was the smallest three-dimensional repeating unit in a crystal. That's a fact. Then we look to how are those unit cells packed together. The closest packing structure is the physical arrangement of any of these parts. Now we're talking about possible molecules, ions, or atoms, right? So we've kind of expanded our discussion from molecules to include everything. The closest packing structure, or the closest packing model, minimizes free space, open space in the crystal. And that's where we start, unit cell and closest packing structure. You try to find, in fact, the closest packing structure is the one with minimum energy. And most natural systems tend toward minimum energy. I think I mentioned that in 213. These two are kind of like the opposite sides of the same coin. That's heads and that's tails. They're related. They use different methods to characterize the crystal structure. So they're not interchangeable, but they are related. They're kissing cousins. Here's an example of a cubic unit cell, right? Represented three different ways. This is a ball and stick model, right? And these are there are more than three, but we're only going to look at three because, I mean, this is not a physical chemistry course. We don't have time to go into that much detail. But the simple cubic model, the unit cell, has the molecule or the atom or the ion, whatever the case may be, at the corners of the cube. So how many of them will there be? There will be 8 in that cube. Okay, the body-centered cubic still has the cube, but it's also got one right in the middle. Okay, the face-centered cube has the cube, right? But it also has an extra component of some kind on the face of every side of this cube. And there are 6 sides to a cube, right? Just roll the dice. How many possibilities are there? 6. 1, 2, 3, 4, 5, 6. This is a lattice arrangement. This is to show you that even though the cube, in this case, is the unit structure, it has to interact with other cubes, right? So when you say, how many atoms, let's say we're just talking about atomic lattice structure, just to keep it simple. How many atoms are possessed by one of these cubes in the lattice structure? Well, look, this one is shared by 1, 2, 3, 4, 5, and there's one above it, 6. So that one has to be split 6 ways. Does that make sense? Let's see. Cut it in half of those 2, cut it in half of these 2. No, it's actually an 1/8. An 1/8 of that atom belongs to that 1 cubic unit. And if you have 1, 2, 3, 4, 5, 6, 7, 8, and only an 1/8 of each one, then that simple cube really only represents 1 atom. I know that's weird. If you do the same thing for this one, it's got 1 atom from the corners, but it's got this one that's wholly belongs to that cube. So this one has 2. If we do the same logic for the next one, we get 1 for the outside and 3 for the inner ones, which means 4. So this represents 1 atom, this represents 2, this represents 4 atoms. The space filling model is like this one. This shows you how in a simple cubic, all of these corner atoms touch one another. Okay? Whereas in this one, they don't touch one another. They only touch the one in the middle. And in this one, they only touch the face atoms. Okay. This is a discussion, Bragg's equation, which was developed by Bragg to help tease out information from regular crystal structures. In other words, if you know the crystal structure is of a certain type, or you're trying to find out what it is, you can treat the crystal as if it were a lens, so to speak. It will take light that enters it, and it will cause the light waves to interact a certain way. And on the other side, your detector will pick up a signal. So the Bragg equation uses this integer. It's just a modifier. And then here's the wavelength of the light.
Hello?
And because the atoms are so close together, the only thing that can really fit between and interact with them is X-rays, really short wavelength. So there's the wavelength of the X-ray. And there's the distance between the atoms. And there's the angle of incidence. So in other words, if you shine the X-ray straight down, you won't get any response. You have to shine it at an angle so that waves come in at different positions and interact before they come out. So that's the equation, and this is what it looks like. So you have this layer of atoms and this layer of atoms, and you got this one wavelength coming in here, and you got this other one coming in. And they interact, and where they reinforce positively, you get an increased strength in the signal. And you can detect that over here, the reflected rays. And the machine, I used to use one for soil research. And the machine has this swing arm on it for your detector. Or the detector's here and you swing the incident rays side, either one. But by that difference in the two, you can tell what is this angle theta. And that angle theta is related to the distance. It's related to the wavelength of the light and the distance between the atoms. So you can tease out information about your crystal structure by just knowing, one, what is the N going to be? The wavelength of your light is given. You may not know the distance, but you can measure the angle, right? So if this equation has all those factors input, except for the D, you can solve what's the distance between the atoms. And that tells you something about the structure. Okay. Now, this methodology, that was the simplest way to do it. The methodology has been used in 3 dimensions. Well, actually, it's 2 dimensions, like this pattern, which is supposed to tease out information about the 3-dimensional structure of the crystal. And it's called X-ray diffraction, because the X-rays are diffracted by the crystal and they give you this pattern. And lots of different molecules, atomic crystalline structures have been elucidated by interpreting the X-ray diffraction pattern. In fact, that is the way that the DNA molecule was deduced, by studying the diffraction patterns of DNA. The real trick for that was to cause the DNA to arrange itself into a regular crystalline structure. That was the hard part. And then the second hardest part was interpreting the diffraction pattern, which is for DNA. Anybody that knows how complex DNA molecules are understands that the diffraction pattern should be a nightmare. But it was done. Watson and Crick got credit for it, but actually the person who did all the work was their lab assistant, a woman who unfortunately died young from cancer. But she didn't get the Nobel Prize for it. Okay, I see I'm down to 1. Well, that's okay. If you have to go, fine. I'll just keep talking, be sure we cover all the topics. What types of crystalline solids are there? Well, I mentioned earlier that you can make a crystalline solid out of almost anything. You can make it out of ions, like sodium chloride, right? You ever spill sodium chloride on a table and look at it with a magnifying glass? Most people haven't, but I have. It's in regular little cubes, right? So that tells you something about the structure of that ionic solid. It's cubic, right down to the unit cell. It's cubic. Molecular solids rearrange the molecules in regular crystalline structure. Now, all molecular solids don't do that, and sometimes you have to coax them into doing that, but it is possible. Atomic solids, yeah, they tend to like to close pack, right? Like metals particular, will tend to pack in a close arrangement. Here's just examples, right? There's a covalent solid that's in a crystalline structure, diamond. Here's sodium chloride, it's in the cube. Water, when it is a molecular solid, when it crystallizes, it forms these hexagonal shapes, and perfect evidence is in any snowflake you ever look at. It has 6 points, doesn't it? That's because of the way water molecules interact when they solidify. Covalent, ionic, hydrogen bonding, which is molecular. Okay, so this comes out of my textbook, looks like chapter 10, and it just organizes the information. So metal ions are going to form metallic atomic solids, and they're held together by delocalized covalent bonds. Network solids like diamond, they're directional covalent bonds. Actually, a diamond with no flaws in it is one single molecule. Group 8A, which is noble gases. They're only held together as solids in some cases by London dispersion forces. Some of them, you can't make a solid out of them. You can't get it cold enough. Like helium. You can make a liquid out of helium, but you can never make a solid. It just, because you can never get to absolute zero. You'd have to go to absolute zero to make a solid out of helium, and we can't get there. Molecular solids, the molecules are discrete, and they're held together by either dipole-dipole or combination with London dispersion forces. And ionic solids are obviously composed of ions, and they're held together by big positive, big negative charges. Okay, we're going to use metal atoms for this closest packing model. So when you close pack things together, you have to assume that the metals are uniform, hard spheres. If we didn't do that, then we're stuck. We can't go any further. So these spheres are packed in layers. And we've used X-ray diffraction and Bragg's law to find out what's the distance between the layers. But they can be packed in different ways. I'm going to show this video now. I hope. It's a long, it has to load up first, I believe. So I hope it's going to, nope, I went too far, sorry. I hope it shows, because it's a good video. Come on. Let me give it a couple more seconds. There we go. Yeah, it had to load a lot of stuff before it could run.
The constituent particles in crystal may be thought of as solid spheres. And in this video, we should...
A word of warning. Tune your ear to an Indian accent. Okay? They speak proper English, but it's heavily accented. So do your best.
Try to understand the close packing of spheres in a 3D space, leaving minimum vacant space. Packing in one dimension. There is only one possible linear one-dimensional arrangement possible with spheres. They queue up linearly, each sphere touching the adjacent spheres like this. Packing in two dimensions. To arrange spheres in two dimensions, we take the linear one-dimension arrangement that was shown previously. There are two ways by which we may arrange the spheres in a two-dimensional platform. They may be arranged like this. Note that each linear arrangement are aligned vertically. Here, the vacant space is this. Now, in this packing, the spheres take up only 52.48% of the available space. Here, a single sphere touches four other spheres. If we join the centers of the spheres, we get a square. Therefore, this packing is called square closed packing. A second way of arranging the linear one-dimensional arrangements is to keep the spheres of the second linear one-dimensional arrangement in the depressions of the first, like this. Here, every alternate linear arrangement has the same alignment. These are the vacant spaces, which is visibly less than the square closed packing and hence more efficiently packed. In this packing, the spheres occupy 60.4% of the available space. The voids created in this packing touches three spheres forming an equilateral triangle and are called triangular voids. A single sphere touches six other spheres, and by joining the centers of these spheres, we get a hexagon. Therefore, this packing is called hexagonal closed packing. Packing in three dimensions. Making square closed pack two-dimensional layers. This is done by placing a two-dimensional layer just above the first layer and so on. All the layers are vertically aligned. Taking hexagonal closed packing two-dimensional layer. The first layer contains red-colored spheres indicating the alignment of the layer. This alignment is called A. These are the void spaces of the layer. We have to place a layer on top of this layer. For efficient packing, we will have to place the second layer in such a way that the spheres are exactly over the triangular voids of the first layer. Only these triangular voids can be covered. The spheres of the second layer are blue in color, which indicate that this layer has different alignment, and this alignment is called B. We can no longer see all the void spaces created between the two layers. In order to overcome this problem, we will make the second layer transparent. Now we can clearly see the two different types of voids created by these two layers. These are called tetrahedral voids, marked by the letter T, and these are called octahedral voids, marked by the letter O. The tetrahedral voids are created by four steps. First, we make the spheres a bit smaller in order to understand the shape. Then we join the center of the spheres by straight lines. The shape is a regular tetrahedron. So the void is called tetrahedral. The octahedral voids are created by six spheres. Here also we make the spheres a little smaller, then join the center of the spheres to get the shape. The shape is a regular octahedron. Placing the third layer. This can be done in two ways. These are the triangular voids of the second layer that are not involved in making octahedral voids with the first layer. By placing the third layer above these voids is one way of placing the third layer. If we do this, we can see that the first and the third layer have the same alignment A. With similar reasoning, we keep a fourth layer on top of the third layer and see that the second and fourth layer have the same alignment B. This pattern of close packing is called ABAB type pattern. We make spheres a little smaller and join the centers with straight lines to understand the shape. It is my belief that this is the unit cell of this close packing because it is the smallest unit that may be repeated to form the entire crystal. The top of this unit cell has the shape of a rhombus having gamma equal to 120 degrees. 3 such rhombus form a hexagon. For a better visual cognizance, this shape is taken as the unit cell of this close packing, which is called hexagonal close pack or simply HCP structure. Another way of placing the third layer is to cover the octahedral voids of the second layer by placing the spheres of the third layer above the octahedral voids made by the first 2 layers. The alignment of the third layer is different from the first 2 layers, and so the color of the spheres have a different color, that is green color. Let this alignment be called C. Using the same reason, we can cover the octahedral voids created by the second and third layers by a 4th layer. It will be found that the 4th layer has the same alignment as the first layer. So this pattern is called ABCA type pattern. Now again, making the spheres a little smaller and joining their centers by straight lines, we get the shape of this packing like this. The unit cell of such a packing is this. This is nothing but a face-centered cubic lattice. So this type of packing is called cubic close pack or simply CCP or even FCC structure.
Okay. Once you tune your ear to the Indian accent, you can follow along. Okay, let's go to the next one. Let's see. Let's see, maybe if I just click on it, it'll go. Yeah, there we go. So the video gave you a pretty good explanation of these different types of closest packing arrangement of uniform spheres. The ABA type, in which the second layer fits into the first, and then the third layer is perfectly aligned with the first layer. So ABAB is that one. It's also called hexagonal closest packing. So ABAB and hexagonal closest packing are synonymous. Then we get ABCA possible, and these now we're in 3 dimensions, remember. So you get first, second, and third layers are not aligned with one another. So you get this one is out of line with that one and is out of line with this one. And you don't, until you get to the 4th layer, do you start getting alignment with the first layer again. ABCA packing. And this is cubic close packing or face-centered cubic. So that unit cell that we saw earlier, face-centered cubic, would be synonymous with the ABCA or the cubic close packing. Okay, and this is just another way of showing how we arrive at the hexagonal closest packing. Let's see. That's odd. When I look at the space filling version, we haven't seen that one before, I don't think. Okay. This one is odd because it's touching the corners of the cube, but we stuck something else in here too. Spread these things out so that these are no longer touching. So I think we've introduced another possibility here, which just goes to illustrate that we're just scratching the surface. This one is definitely cubic closest packing, A, B, C, A. And the coordination number, what do we mean by coordination number? If you pick one atom, how many other atoms are touching it? In this example, let's see, let's go back. In this example, you have 12 in this face-centered cubic closest packing, or I think it's called hexagonal. Excuse me. No, face-centered cubic, pardon me. ABCA is face-centered cubic. But in the hexagonal closest packing, let's see, cubic closest packing, that's this one. Okay, that's ABCA, cubic closest packing. We have 12 neighbors, so the coordination number is 12. So now this is the discussion. I mentioned this a little earlier. The net number of spheres in each of the unit cells. So if you have a face-centered cubic, we find that each of the corners is worth 1/8 of a cell, and each of the faces is worth 1/2, so we end up with 3. Okay? There. We end up with 3 there, and 1 plus 3 is 4. So 4 in a face-centered cubic. The number in a simple cubic, we did that before, it's equal to 1. And in a face-centered cubic is 4. We skipped the body-centered, which should be 2. Yeah, we skipped that one. But this one's 1, that one's 4, and then in between, the body-centered cubic is 2 atoms present in the unit cell. So why are we doing this? Well, there are a whole host of reasons why people have investigated these structures. But one thing that we can draw from it is if we know the arrangement of atoms in the unit cell, we can deduce the radius of the atom, right? So when you see a periodic table that has indicated in it various atomic and ionic radii, this is one way that they can get that information. So you just need to know the size of the unit cell, the length of an edge, and if it's a simple cubic, the length of the edge is simply 2 times the radius of the atom, remember? Because the atoms from the cube, they're touching. So 1 radius here, 1 radius there, the distance on the edge of the cell is 2 times the radii of the cell. That's an easy one to do. Now in a face-centered cube, the length of the edge, and we're not going to take time to draw this, but the length of an edge is the radius of the atom times the square root of 8. So if you know the length of the edge of your unit cell, you can deduce the radius of the atom. Body-centered cubic, we can do the same thing. And this is, I've got extra documents that explain this. I'm not sure if they're in Blackboard, but I can get them to you if you're really interested. Is the length of the edge of the cell is now equal to the radius times 4 divided by square root of 3. Okay, another thing you can do is once you've determined the radius of the atom, and you combine other information that you can get, like the mass, you can and the edge on the cube, how far is it, which gives you the radius of the atom, and the structure of the cube, the unit cell, you can deduce the density of the metal, right? And here's an example that I worked out. The density of silver is 10.5 grams per cubic centimeter. And these are the steps that you would go through to solve that problem. So if we know that it's cubic closest packing, we know that there are 4 silver atoms per unit cell, which means that in one unit cell is represented only by 1 atom. Remember? For the cubic cell, well, wait a minute, for the face-centered cubic, pardon me, face-centered cubic is 2 atoms. I misspoke, as they say in the government circles, political circles. So we know that the volume of the unit cell is the edge cubed, and we know that the edge then is determined to be 409 picometers. So what's a picometer? Well, a micrometer is 10 to the minus 6th, a nanometer is 10 to the minus 9th, a picometer is 10 to the minus 12th of a meter. So we find that the volume of the cell is this, all right? So why is that important? Because the density formula says this. There's the volume of the cell. Now what we want to do is find out what mass of silver is represented by that cell. Well, we know that there are 2 atoms in there, and we know the molar mass of silver, so we can use that to determine, let's see, face-centered cubic. Oh, I misspoke again. I was thinking body-centered. There are 4 atoms in a face-centered cube. And this is the molar mass of silver. Okay. So we can use that information and determine that this top part here determines the mass of 4 atoms in that unit cell, and we calculate 10.5 grams per cubic centimeter. So in this case, it comes out exactly to the measured amount. In green, that's the measured density of silver. You just weigh it on your balance and determine the volume. Maybe you just take a chunk of silver and drop it in water and find out what the difference in volume is. There you go. Then what's the mass of that silver? Calculate it. So 2 different methods give you the same answer. So we're not going to spend a lot of time on this. There are several bonding models for metals, right? We've sort of put everything aside now, and we're talking about metals. Originally, the electron C model just says that there are metal atoms scattered throughout the chunk, and they share electrons. It's just like in a sea of electrons that surround all these atoms, and that holds them together. But of course, that model fails more often than it succeeds. So it wasn't until the molecular orbital theory came along and was applied not just to covalent compounds, but to these metals, that the band model arose and is a better interpretation. This is the C model, and this is the molecular orbital model applied to metals. So for the entire chunk of metal, you take all of its atomic orbitals, mix them together, and you come out with molecular orbital models, molecular orbitals. Same number, but you fill all of them with the electrons that are available. And when you do that, you find that the continuum of energy from low to high, well, I just said it, it's a continuum. There are virtually no breaks if you have enough atoms. This is a mole of atoms, has a continuous energy band for the that mole of atoms. There's really no separation. So it's very easy for an electron to move from one level to the next. That's why metals are very good electrical conductors, right? They can move from one energy level to the next with very little push. I'm not going to spend any time on this one. Sorry. So what do we do with metals? Well, you can have pure metal, right? If you want gold bullion or silver bullion. But if you want to make a coin that'll hold up under wear and usage, you need to form an alloy, something that will strengthen the metal. So that's why usually silver, well, before 1974, I think, all coins were a mixture of 90% silver and 10% something else, usually copper. And that copper in there strengthened the silver metal so it would hold up under daily use. Well, that's called an alloy. It's actually a solution of two metals. And these alloys can be characterized in two different ways. One is a substitutional alloy. In the substitutional alloy, you have the pure metal, and you just kick out one of the metal atoms and stick something else where it was. Substitutional alloy. So in brass, which is mostly copper and some nickel, you just take a copper atom out, stick a nickel atom in. And that's your substitutional alloy. Interstitial alloys are those where, you remember in the closest packing model, you have these voids, spaces in between the atoms. Even if they're close, really packed close, you still have some space available. If you pick a small enough atom, you can stick it in those spaces. That's an interstitial alloy. A perfect example of that is steel, where you have iron and you stick carbon atoms in those voids. It doesn't take much. A 0.5% by mass of carbon with iron gives you what's called high carbon steel. And what the carbon does is it locks the crystals in place, because very often in crystalline structures, if you apply enough shear, you can move the crystals side from side. But if you put something in there, just the right ingredient in those interstices, they will lock those crystals together. And high carbon steel is very hard. It's not deformable. And when you sharpen it, it will hold an edge. Of course, it's still iron, basically. So it will rust. It will corrode. So that's why high carbon steel that has no other components in it to protect it will rust easily. And you have to take care of that blade. We can put other things in there. In fact, you can make steel that's both interstitial and substitutional. So we put chromium in there in place of some of the iron. Originally, we put the first inventor of stainless steel put 35% chromium in. And now we find that 11% is plenty. And what happens is that chromium is much more reactive with oxygen than iron is. So what it does is it forms a skin right on the surface of the metal instantaneously, very thin. That's why when you polish stainless steel, it stays shiny, because the layer of chromium oxide is so thin. But if you scratch it and remove some of that, the repair is instantaneous. So oxygen never has a chance to get down into the, to react with the iron. And even if it did, there would be other chromium down there to suck it up. Okay, those are the two types of alloys. Here's an brass is substitutional, steel is interstitial. I've already talked about those. This is an example of a network solid. Now these are carbon allotropes, right? They're still pure elements, but they have different structures. That's what an allotrope is. For diamond, you have this network solid, right? Where these are all covalent bonds. With graphite, you have covalent bonds in layers, right here. And the bonding, the intermolecular bonding between the layers is very weak, right? So it has to be van der Waals, excuse me, I'm reverting. It has to be London dispersion forces, right? Because all of these carbon atoms are the same. You can't have any dipoles. So the only thing available then is London dispersion forces, and that's what holds the layers together. And that's why graphite is often used as a solid lubricant, because they slide past one another. And these solid lubricants are especially useful where you don't want dirt to get into the system. You don't want any type of contamination. So you close off the system and you put this graphite in there. We used to do it in the, for my motorcycles. I used to ride dirt bikes. And you would open up the cam on the end of your cable and expose the interior of the cable. And you have this can of graphite with a small tube on it, and you'd open it up and squirt it in there. And then you would set it back down. And that graphite would lubricate the cable, but since it's not wet and not wettable, it won't attract dust. Okay, so here's why diamond is a poor insulator, is a very good insulator, and why metals are not good insulators. The filled molecular orbitals in a metal are very close in energy to the empty molecular orbitals. So promoting electrons into this empty molecular orbitals is very low energy. So you can move electrons very easily. But between diamond, the filled molecular orbital energy distance between that and empty molecular orbitals is very high. And that's one way that diamond is deduced or differentiated from paste jewelry, fake diamonds. All you have to do is test the thermal conductivity. So they have this device, every jeweler in business has a thermal conductivity detector, and they just take your diamond and press it against it and measures the thermal conductivity of the stone. And unless it's high enough, a certain level, you don't have diamond. Okay, so we talked a little bit about delocalized electron densities and in our molecular orbital discussion. And this is just another way of looking at graphite. The really strong bonds are here in this hexagonal structure. And the weak bonds are between the layers. Now, what's a ceramic? Ceramic is an operationally defined material. So you just characterize it, and you don't really define it in terms of molecular structure. Ceramics are typically non-metallic materials, right, which means they are very strong, but they're also brittle. That is, they're not tough, which means if you want to use them in a situation that needs toughness, they have to be backed by something. But they are extremely resistant to heat and aggressive chemicals. In fact, ceramics were used on the surface, most of the surface of the space shuttle. because they were heat insulators. In other words, if you have a ceramic brick on the surface of your space shuttle and the temperature outside is 2,500 degrees Fahrenheit, the heat is not going to be efficiently transferred from one side to the other. So in effect, what it does is all that heat is sloughed off with the air passing over it. So that the friction of the air creates the heat, and as it's moving, air also takes the heat away. We typically make ceramics from clays, which are basically silicates or aluminosilicates, and they are finished by firing at high temperature, which changes their structure. Semiconductors. In order to define a semiconductor, we have to know what a conductor is, right? Conductors and non-conductors. Those materials are used in electricity. Conductors are like copper wire. Insulators are like the wrapping around the wire, the plastic wrapping. Conductor versus non-conductor. Electricity goes easily through copper. Semiconductors are kind of in between. Sometimes they can conduct and sometimes they can't. And that selectability is key to the semiconductor industry, or the formation of microchips and computers and logic circuits and all of that stuff. You can have two types of semiconductors. But first, you've got to start off with a base material. And the cheapest base material for semiconductors is silicon. So we have silicon here, and it's pure. That may not be an accurate representation of the structure, but they do occur in multiple layers and probably connected to one another. And it needs to be very pure. So how do we get it to behave in a semiconductor? I mean, not a semiconductor, in a logic circuit of some kind? Well, you have valence electrons, of course, for silicon, just like any element. And what we want to do is modify the crystal so that it is either excess electrons or deficient in electrons. If it's excess electrons, we have an N-type semiconductor. So how do you get an N-type? Well, you substitute, make an alloy of some kind, you substitute for the silicon an element that is close by but has more valence electrons than silicon does. So if you look on your periodic table, here's silicon, and more electrons are to the right, okay? So we could dope it with phosphorus or even arsenic. Let's keep it simple, just right or left. So let's say phosphorus. So we put phosphorus in here. Now you have a net excess of one electron. And you have an N-type semiconductor. Not just one of them, of course. The industry has developed standards for how much you put in. The other option is a P-type, or a positive type semiconductor. So you put something in there that is deficient one electron from silicon. So that gives us the P-type. So now we take our periodic table and we look at silicon and we go to the left. So you can put aluminum in there or gallium, something like that. So let's keep it simple and put aluminum in there. Now you have a net positive because we're deficient in one electron in that region. Now, I'm not going to go into any details about how they work. That's just how we make them. How they work is a science unto itself with many sub-disciplines. This is a molecular orbital explanation of what I just talked about. When we have a p-type semiconductor, we often discuss the movement of electrons in terms of, for the n-types, excess electrons, but for the p-types, we say the holes are moving. Okay, so when you have an absence of electron, we call it a hole. And this is a conceptual way of understanding what's happening in the semiconductor and between two different types of materials. Because you may put an n-type on one side, slap up against it a p-type, and form a diode. Okay, so this is a further explanation based on what I just told you. You can look at it yourself. How about ionic solids, right? Ionic solids like sodium chloride, or, you can think of almost anything. As long as you have a positive ion and a negative ion, at least one of each, then you can have an ionic solid. But the ionic solids, we may write them this way. But that's really just the simplest ratio of sodium cation to chloride anion. The reality is that you have a network of sodiums and chlorines together in that crystal structure, in that lattice. But they typically have very high melting points, right? If it's a solid, then it takes a lot of energy to break those apart. Now, of course, if you put them in solution, the action of the, say, water is sufficient to tear that crystal apart. So it's odd that at room temperature, you can put salt in water and just destroy the crystal. But if the crystal is intact, it takes a monstrous amount of heat to drive those ions apart. So you can imagine how much energy is being supplied by water. So if we have differences in melting point here between two different types of ionic solids, why is it? Well, you have inter-ionic forces, okay, so that's what holds things together. So the larger the force, the higher the melting point. So now we need to say, all right, what influences the strength of that force? Well, two things. What's the charge difference? Right? If you have a large charge difference like this one, magnesium oxide, the forces between them will be stronger. It's purely electrostatic. 2 pluses against 2 minuses is a stronger attraction than 1 plus against 1 minus. And the other thing is, what's the distance between the ions? Right? What's the radius of each of these ions? If they're both small, then you can get those ions closer together. And remember, electrostatic attraction is proportional to the size of the charge and inversely proportional to the square of the distance between the two. That's Coulomb's law. So if you bring them closer together, the strength of the attraction increases way, it goes up by the square. So that's why the melting point of magnesium oxide is very much higher than sodium chloride. I'm surprised I didn't put the actual values in here, but trust me, magnesium oxide melts at a much higher temperature than sodium chloride. Okay, The video that we saw earlier talked about the different types of voids. This is a trigonal hole. When these three touch each other, and this type of hole is based on 2 dimensions, or at least this one is based on 2 dimensions, because we're only looking at one layer. That's a trigonal hole. You need something? Okay. When we start getting into 3 dimensions, and we say this is a tetrahedral hole, simply because 4 atoms touch one another, or 4 ions touch one another. And if you look at the centers, they're evenly spaced at the points of a tetrahedron. These guys in octahedral holes in hexagonal closest packing give us the octahedral hole. And all you have to do is connect all the centers of these, and you find that it's a regular octahedron. So the octahedral hole is associated with hexagonal closest packing. Okay, so what about the size of the holes? The largest one is the octahedral. That hole is the biggest. Tetrahedral is the next size down. Trigonal is the smallest size hole that we can get. I'm going to let you look at these on your own. It just puts everything into a single table. Types and properties of solids. We've got atomics over here, molecular here, ionic here, and it gives you the structural units, types of bonding, typical properties, and examples of each. Now we're gonna, I'm really running long, so if you gotta go, you won't hurt my feelings. Now we're going to talk about how do liquids behave in terms of their physical properties. So if we put a liquid in a closed container, the closed container can have a liquid in the bottom, and what happens is when you first put it in there, there are not too many of the liquid atoms in that headspace above, right? So all the exchange happening is one way toward the vapor phase. So you have atoms moving into the vapor phase. But gradually, as more and more of those vapor phase atoms accumulate in the headspace, they start to return, right? So you get backwards and forwards, liquid, gas, gas, liquid. And you reach a point of equilibrium where the rate of return is equal to the rate of vaporization. Condensation equals vaporization rates. Now you're at equilibrium. And for each liquid, the pressure that develops in that headspace is characteristic of that liquid. So guess what? The weaker the forces, the intermolecular forces for the liquid, the more of them escape into the headspace and the higher the pressure. So for weak intermolecular forces, the liquid produces higher headspace pressure. This is what it looks like on a graph over time. The rate of evaporation is pretty much constant to begin with, but the rate of condensation eventually catches up with it, and that's where you reach equilibrium. Okay. What's the vapor pressure of water at 100 degrees centigrade, 1 atmosphere. Oh, I thought it was going to tell us how we know. How do you know? Because when you reach 100 degrees centigrade, what happens to water? Well, if there's 1 atmosphere pressure and it's boiling, then you know that 1 atmosphere is bearing down on the top as 1 atmosphere is forcing atoms off the surface. Now, if we put water in a vacuum and decreased the headspace pressure, right, to a fraction of an atmosphere, say 1/100th of an atmosphere, then the vapor pressure would be that, but the temperature would also be less until it reached equilibrium. Another way of determining vapor pressure is you got a barometer. If there's a vacuum up here at a sea level, the pressure is going to be 760 torr, 1 atmosphere. If you put a little water up here, and we keep the temperature the same for everybody, then at standard temperature, which I believe is 25 degrees, then there will be enough water vaporized here to decrease the reading on your barometer to 736 torr, which is a difference of 24 torr. So the vapor pressure of water at this temperature is 24 torr. If you use ethanol, then the vapor pressure is 65 torr. If you use diethyl ether, the vapor pressure is 545 torr. And that all of these differences in vapor pressure depend on what's the size of the intermolecular forces. Water has very strong intermolecular forces. Ethanol has less, and diethyl ether has much, much less. Which means the lower the intermolecular forces, the higher the vapor pressure. They're inversely proportional. Oh, so the vapor pressure changes and increases, in fact, significantly with temperature. Why is that? Because if you add energy to the liquid, you're breaking those intermolecular bonds. And that means that the molecules at the surface of the liquid are free to evaporate. And this vapor pressure versus temperature curve varies depending on the material. So water, vapor pressure goes up like this in a steady curve until it reaches 100, and then it boils. And at that point, the temperature doesn't change anymore until all the water is gone. Ethanol goes up faster until its boiling point is reached at 78.4. Diethyl ether goes up even faster until it boils at 34.6. Okay? So if you put diethyl ether in your hand, with a glove, of course, then there's sufficient warmth from your body to boil it in your hand, because body temperature is 37 degrees centigrade or Celsius. And that's sufficient to boil diethyl ether. Okay, so what do I have here? Well, what I have here is, I believe, a Arrhenius equation. And let's see. No, that's Clausius-Clapeyron, excuse me. Clausius-Clapeyron. And what this equation does is it relates the enthalpy of vaporization to the vapor pressure, right? So if you have knowledge, well, this is the differential equation. the integrated equation works better. It's easier to handle. So down here, we find that the natural log of the vapor pressure is equal to the negative of the enthalpy of vaporization. The enthalpy of vaporization is an indicator of how strong the intermolecular forces are. The higher the delta H, the stronger the forces. Okay? And then this occurs at a given temperature. And then you have a proportionality constant. Well, that still doesn't help us much because we don't know what that constant is. We know what R is, and we can measure vapor pressure, we can measure temperature, so we can solve for the delta H if we know what C is. But suppose we don't know what C is. Then what you have to do is conduct the experiment at 2 different temperatures. And if you do that at 2 different temperatures, then you can use this modified integrated equation. There's temperature 1, there's temperature 2, and this just combines them at the end. So temperature 1, temperature 2, 2 different measured vapor pressures. Now we're in business. We don't need to know what that C constant is. Okay. So there's the Clausius-Clapeyron equation that is most useful. And notice that the R is the universal gas constant with the energy term, not liter atmospheres, the energy term. Okay. Why? Because H is in terms of joules also. So if we know these values from our experiment, we can plug them in to our equation and find out. All we need is one unknown. And in this case, we were solving for what's the vapor pressure at a different temperature. If we knew the heat of vaporization was 43.9 kilojoules per mole, we plug it into the equation along with these other variables and find out that the expected vapor pressure is 194 torr if we increase the temperature of water from 25 to 65 degrees centigrade. Now, what does this graph represent? If we heat ice and we measure the temperature at the same time, then as we add heat gradually, we find that the temperature of the ice will increase until it reaches its melting point. When it reaches its melting point, now the heat that we add is not just used to raise the temperature, which is what was happening before. Now the heat we add is used to break bonds and convert the solid into liquid. And it's going to stay at that temperature until all the solid is gone. Then once all the solid is gone, the energy we add in the form of heat is used to raise the temperature of water, the liquid water, until we reach the boiling point. And now the energy, instead of exciting the water molecules in liquid state, is sufficient to cause the water to leave in vapor. And at that point, we stay at that temperature until we reach the point where all of the water is gone, all the liquid is gone. And now we have steam. And if we have the proper equipment, we can continue to heat that steam, add energy to it, and it'll absorb it. And there are many industries that use superheated steam to transfer energy from one point to another in their plant for whatever process is being worked. Okay. So which would you predict to be the larger for any substance, the heat of vaporization or the heat of fusion? Think about it. What bonds are being broken and what is the result? Heat of fusion is the amount of heat required to convert solid into liquid. So you know that if you add heat to a solid and make a liquid out of it, all you've done is broken down the crystal structure and the atoms or molecules are still close together. They're just moving around a little bit. So that doesn't take much energy. But heat of vaporization, you break the liquid molecules free from all other intermolecular actions in the liquid. That takes a lot of energy. Okay, so what's a phase diagram? A phase diagram can be very simple or it can be very complex. But what it does is these items are included, but they don't make any sense until I show you what one looks like. So this is a phase diagram for carbon dioxide. Temperatures on the x-axis, pressures on the y-axis, and we measure various points along here, temperature and pressure, where in this case we have gas and solid interfacing. They're in the system at the same time. So if we cross that line, we go from solid to gas. And everybody has seen that before. If you've seen dry ice on a hot summer day, you will see solid carbon dioxide change directly into gas. It's called sublimation. The opposite of sublimation is deposition. Go from gas to solid. If we go from solid to liquid, it crosses this line. And if we go from liquid to gas, it crosses that line. Now, along this line, you have liquid and gas together at the very same time. If you follow this line, anywhere along that line, you have solid and liquid together at the same time. And down here, you have solid and gas at the same time. There's one point on this graph, the triple point, where you have solid, liquid, and gas, all three at the same time. And it only happens at this temperature and this pressure. Okay? The other interesting point on the graph, and most phase diagrams have this, is the critical point. Past this critical point, any of this space out here, in fact, up here or out here, at that temperature and pressure, which are usually very high, you have a supercritical fluid. And the best way to define it is it has some characteristics of liquid and some characteristics of gas. That's a supercritical fluid. It's very useful, right? Supercritical carbon dioxide is an extremely effective extractant of living material, as opposed to using a solvent and heating it up and actually destroying a lot of the molecules in the process. Supercritical fluid extraction leaves the cells intact in a living tissue and removes everything, almost everything that's not held down. Oh, excuse me. Okay. Now, normally, notice the solid liquid line slopes to the right. So if we were to hold the temperature constant, say right in here, and we go up here like that, and at that temperature we decrease the pressure, at some point we would cross from solid to liquid. Or we would keep going from liquid to gas. Okay? Or if we held the pressure constant and we moved the temperature, we could go, by increasing the temperature, go solid to liquid, or from here go solid to gas. Okay? That's a common characteristic of phase diagram for any substance. There are a few, like water, that defy that norm. The solid liquid slope of the line is negative, not positive. So that says at a given temperature, if you decrease the temperature from liquid, you go from liquid to solid rather than solid to liquid. Okay, we're about done. So under what conditions here would the intermolecular forces increase? And what happened? Why is that true? What happens to each of these following properties when the intermolecular force increases? If you increase the intermolecular force, the boiling point should go up because there's more force holding that liquid together. It takes more energy to break those bonds. Right? Viscosity. As you increase the forces, the viscosity increases. It's holding them together, it makes them thicker. Surface tension. Increase the forces, increase the surface tension. More force holding that skin taut. Enthalpy of fusion. That is, how much energy is required to go from solid to liquid. The enthalpy of fusion will increase as the intermolecular forces increase. Freezing point. The freezing point will also increase as more energy is required to melt the substance. Vapor pressure. This one takes, you have to stop and think for a second. Vapor pressure, if the forces are higher, it holds the liquid together and decreases the vapor pressure. And the heat of vaporization also increases. So the only one where the relationship is inverse is vapor pressure. Everything else is a direct relationship with intermolecular forces. And that's it. It's about time. I've gone an hour and 15 minutes over. Okay. So I got one student left. You have any questions? Okay.
No, I don't.
So if you have any questions in the meantime, you know how to get in touch with me. And we'll, next time we'll meet to discuss chapter 11 in my book, chapter 13 in your book. And hopefully by that time, everybody will have their lab notebook and have it basically set up so that you can get that first lab notebook check done.
I got mine. I bought 2 last semester when I found them. That way.
Okay, that's smart.
Yeah.
And then before you can do the first lab experiment starting on the 5th of February, you need to set that one up and send me photos or scans or whatever you have available so that I can grade it and release the video for you.
Right.
Okay, have a good week.
You too.